Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem. Find the longest substring containing vowels in even counts. Vowels are these 5 special characters, A, E, I, O, U. I guess we're not including Y this time. Those 5 characters. Now, in this example, it looks like the longest substring is going to be this in that case, because if we can see how many E's do we have, it looks like we have exactly 2 E's. That's an even number of E's. How many I's do we have? It looks like 2 I's, an even number. We also have 2 O's, even number. It looks like we don't have any A's, and I don't see any U's unless I'm blind or something. Why can't we make it bigger? Well, if you try to increase it going towards the right, we get an O. That will give us 3 O's. That's not a valid string. I mean, maybe we can find another O, but we can't. We can get this E, that gives us 3 E's. We can also get this E over here, that'll give us 4 E's, but we can never find a match for the O. Okay, so that's the problem. Clearly, there's a brute force solution, just go through every substring, that would be n squared, but can we do better? My initial thought was to do something like a sliding window, but you quickly realize that, okay, like let's say at this point, I'm at 3, I have 3 E's. The whole point of the sliding window is at some point you have to shift the left pointer, but in this problem, there is no way to know that we shift the left pointer because, okay, we have 3 E's. Well, we could shift the left pointer and then get a substring with 2 E's, sure, but how do we know that we're not going to see a 4th E somewhere along the line, and then maybe we should have kept the pointer over there? So actually, sliding window is not very intuitive for this problem. I mean, I just kind of showed you why it might not work. I kind of talk about having a bunch of algorithms in your bag of tricks, and you want to be able to quickly verify that an algorithm will work or quickly confirm that it won't work so that you don't waste too much time. And so now I quickly eliminated sliding window from this problem. Now let's dig deep into what exactly the problem is asking for us. Yeah, if we just look at it from a naive perspective of substrings, that's not going to help you out. You really have to understand the constraints of the problem. We want an even number of each character. So as I kind of showed, okay, at some point we might have an odd number. In that case, what we could do to make this valid is remove exactly 1 E, right? We just want to move exactly 1 E. But there could also come a point, suppose this substring over here, we have 2 I's, we have 3 E's, and we have 1 O. So for this substring, what I'm getting at is as we shift our pointer, we're going to have, let's say, a pointer I, it's going to tell us the end of our substring. So now we want to know, ending at this substring, what's the longest substring we could create? In other words, we want to know, well, what would be the beginning of the substring? Well, if I have an extra O and I have an extra E, I have to eliminate an E and I have to eliminate an O. Well, where was the first O that occurred from the beginning of the string? Where was it? It was literally right here. So what would be the longest valid substring ending here? Basically, like this is our, let's say, right pointer, and we were trying to figure out where the left pointer would go. It's also going to go here. So we're going to do right minus left, and that leaves us with a substring of length 0. So ending at here, the longest valid substring we can create is of length 0. Now, allow me to crush your spirits and tell you why that solution actually won't work either. Imagine we had an A, and then another A, and then we had an E, and then we just had like some random characters. And then let's say we had 2 occurrences of O. So imagine we had a single pointer. It keeps going. Now, by the time that we get here, we have an even number of O's. Actually, let me redo this example. All I did was swap these 2. So we're back here, 2 O's, 2 A's, but we have an extra E. So you think you're being clever. I thought I was being clever. Just say that, okay, we want to remove the first occurrence of E, therefore our window will pretty much be like this, right? So our window is valid. We removed a single E. Well, we also removed a single A. We had an even number, now we don't. So that's why this solution won't work. So how do we solve the problem then? Well, it's going to be a bit more brute force than you'd expect. Remember that our string could have characters that technically aren't vowels either, so keep that in mind. We know at the very least for every single character, for every vowel that is actually, we should track whether we have an even number or an odd number. That's going to be pretty easy to track. There's only 2 possible states for each character. We could have a counter, we could increment by 1 each time, but after we do that, let's just mod it by 2 for simplicity. Now, assuming we have that, we're going to leverage the ideas of the previous solution. Back to this example for a second. Imagine that we're at the right pointer. The state of the vowels is this: even number of A's, odd number of E's, even number of O's. So what we want to do is remove the minimum possible prefix from the beginning such that our window is valid. In other words, what does the prefix of the window have to look like? Well, we have to guarantee that that prefix has an odd number of E's. We also have to guarantee that that prefix has an even number of A's. When I say even number, remember that 0 is an even number. So that's the reason why when we try to remove this prefix, we're removing an odd number of E's. That's good, check mark. We're removing an even number of O's because there aren't any O's in there, check mark. But wait a minute, we wanted to remove an even number of A's because we have an even number of A's. In other words, like we have 2 A's in the entire thing. But if this prefix has an odd number of A's, we just screwed ourselves. So if what we're saying is we want to ensure that the prefix matches this criteria, and this criteria is what this entire string also is, we're basically saying that like the count, however we determine it, whether we determine it with a hash map or possibly, given the fact that the character set is lowercase a through z, we could also use a bit mask. However you want to determine the state of the string, we just have to make sure that the prefix that we remove has the exact same state as the entire string ending at this position. I know that's kind of complicated. I know it's clever, but when you actually draw it out, when you actually go through an example, this specific example that I came up with, I don't think this is a test case on Leetcode, correct me if I'm wrong, you will arrive at the optimal solution. So that's the problem. That's how we solve it. Make sure that the prefix has the same state in terms of odd and even for each vowel as the entire thing. And of course, we're looking for the minimum possible prefix that does that. So how do we track that? How do we know the minimum possible prefix that has this state? How do we do it? Well, just like this. Suppose we're tracking it with an array or even like a hash map like I showed. What we would say is that this is the first time that we've found a hash map that has this state. A is an odd number and the rest of the characters, the rest of the vowels actually are an even number. The initial state, like the initial prefix, like an empty prefix, technically has an even number of every single vowel. Honestly, I could go more into the theory, but it'll probably just make more sense if I do an example. And then once I do that example, you'll see why we don't need an array or a hash map to track the count of each vowel. We can actually use the data structure we talked about a couple days ago, or maybe yesterday, I don't remember, the bit mask. So this is what we're gonna do. Go through each character. Okay, now we see an A. So now within like my current count, my state, I'm going to say, okay, A is now an odd number. Remember how I said for each character, we're going to be mapping it to the first occurrence of that character because that might be a viable solution? Well, it turned out that that wasn't the correct approach, but the correct approach is similar. For the current state, the hash map, or what I'm actually going to end up using to code this up, is the bit mask. For each unique occurrence of that bit mask, I'm going to map it to the first time that we saw it. So right now, this is the first time that we saw this bit mask. So remember that all of these are 0. So this is the first time we saw this bit mask. We're going to map it to index 0. This was the first time we saw it. So if we ever need it again, for example, if we ever got to a point like this, where we have 3 A's, pretend like this isn't a vowel for a second, we would know that we can remove this prefix and then this thing will be valid. So that's the whole idea. Now, it's kind of hard to code this up, like to visualize this. So just assume that this is how I'm going to draw it. Like this is how it would look like in the bit mask, for example. And we're saying that that was mapped to index 0. Now I'm going to get to E. Now I'm going to say, okay, well, E is an odd as well. And so now our state looks slightly different. And we're going to say, okay, well, that state was mapped to index 1 over here. Now I'm going to get to A. Well, I'm going to increment this by 1, but I'm not going to set it to 2. I would rather set it to 0 because we know it's even now. So this is the first time we've seen this bit mask as well. I realize I just drew this one wrong. This should be a 1. I'm really sorry about that. But this is the first time we've seen this one, which is this 0, 0, 1, 0, and this maps to here at index 2. Now we're here. And since this is a non-vowel character, we want to ignore it. We don't want to update the count here. And so now this hash map thing, this count, this bit mask stays the same. So what should we do? Should we say, okay, well, this is the first time we've seen it, so this should map to index 3? Should we rewrite this part? No, because we would never want to remove this prefix because it's the same as this prefix. So we would always want to remove the smaller prefix. So this can stay the same. Never change any of these mappings once they've been written. So now we are here. Once again, this is a non-vowel. It's not going to do anything. Everything stays the same. Now we're seeing a vowel. It's O. This guy will change to 1. This is the first time we've seen this. So I'm going to do 0, 1, 0, 1, 0. By the way, when I'm doing this, I'm making this the most significant bit, and this is the least significant bit, though it doesn't really matter. You could have reversed it if you really wanted to. Now, so this maps to this index, which I believe is 5. And by the way, I guess I forgot to mention, when we were over here, what was the longest valid substring we could have created? Well, we're at index 5. We're going to see, have we seen this state before? Yes, we have. It would have mapped here. It would have mapped to index 2. Sorry, this is index 4. This is index 2. So we're here. This is the same state, and we've seen that one before. It was here. So what's the longest valid window we could create up until this point? It would be 4 minus 2, which is this section over here. So now continuing, when we're over here, since this is the first time we're seeing this state, we're at index 5. We're going to look it up. We're going to do 5 minus 5 because this is not valid. We do not have a valid string ending at this index. It's impossible. We have an odd number of O's. We can't remove anything from here that has an O. So now we get to this index. We're at index 6. We're going to update the count of O. This is going to go down to 0. So now you tell me, have we seen this state before? 0, 0, 0, 1, 0. Yep, we've seen it here. That tells us index 2 once again over here. What that tells us is this is the minimum prefix that you remove to make the substring valid ending at this index. And the length of it, of course, is going to be 6 minus 2. That's 4. So that's the dry run. I think it makes sense why it works. The only thing that I'm going to mention that instead of using a hash map or an array to count this, we are going to use the data structure called the bit mask. The reason for that is mainly just because it's easier to code up and it's slightly more efficient. You theoretically could use something like this or an array. I believe in terms of big O time and space, it actually would be the same. It's just you would probably have to implement some logic to do the comparisons, whereas a bit mask is actually just a single integer. So doing comparisons with that is very straightforward. So just to quickly review, remember an integer has 32 bits. So what we want to do, given that we have a character set of lowercase a through z, that's 26 characters. So we have enough bits in a 32-bit integer for each of these characters to be set. But remember that we don't actually care about all of the characters. The only thing we're counting are these 5 characters, which are the vowels. So actually, we only need 5 bits. So the way you could naively code this up is perhaps lowercase a would correspond to like the first bit, the least significant bit, and then e would correspond to whatever integer it corresponds to in the alphabet. I think it's 5 or 6 or something. But that'd be the naive way, and that's actually easier to code up. But the smarter way to code it is by putting all 5 bits stacked together in the same position. I guess I wouldn't even say it's the smarter way to do it. They're both the same in terms of big O runtime and space. It's just that the second one is going to be slightly more efficient. So I'll show you both ways and I'll let you decide. The time complexity is going to be O of n because we're just doing one pass through the input. The space complexity is a bit more interesting given the fact that, first of all, this mapping, we're going to do it with a bit mask, so it's going to be constant space. But even if you did it with a hash map, I mean, it's only going to be 5 characters you're keeping the count of, so it's not going to be very inefficient. But what about down here? At first, it seems like we could have a variable number of states, right? Since we're using those 32 bits, we could have up to 2 to the power of 32 different states. So theoretically, that might not be efficient. But remember that we're only using 5 bits. And what are all possible combinations? Well, it's literally 2 to the power of 5. What's 2 to the power of 5? That's 32. There are 32 possible states that we could possibly be in. So even the space complexity is pretty efficient, as you can see. So we're going to keep track of the vowels. Now we could throw these into a hash set, but really for a string of length 5, I don't think it's going to make a difference. So we're just going to use this to look up a character to see if it's a vowel or not. We're going to have our result initially. We're going to say that's 0. That's going to be the length of the longest substring. That's what we're going to return. We're also going to keep track of the current state within our bit mask. We're only going to use 5 bits of this. And for every mask, we want to map it to the first index that it showed up at. Now, one default mask is 0. Where does 0 show up at? Like the empty bit mask, which technically has an even number of vowels. Well, we could say that that maps to -1 because, for example, like let's say the string started as like 1, 2, 3, 4 X's. We would get all the way through here. We'd say, okay, right now we're here. This is of length 4. We want to remove the prefix that has the same state as this one. This one has an even number of every single vowel. What was the first substring that had an even number of every single vowel? Well, technically an empty substring. And so therefore this index is technically 3. From that, we would subtract the first substring that had all even vowels, which was at index -1. So 3 minus -1 is going to be 4. That's why the math would work out. Continuing, let's just go through the input string, and we're going to need the index. So I'm going to use enumerate in Python. If you're a beginner, you might want to check out my Python for Coding Interviews course where I go through all this stuff. We want to update our mask right now. What we want to do is something like this. First, we want to compute the position of the character. So ord of this minus the lowercase a. And we only want to do this if the character is in vowels, if this character is actually a vowel. So this will tell us which bit to set in the bit mask. How do we set that bit? Like, let's suppose this is our state of our bit mask right now. Well, at first you might say use bitwise OR, because let's say the bit we're trying to set is this. Using bitwise OR, we'll set that bit, sure. But what if that bit was already set? It's 1. Remember that we want to keep track of even and odd. If it was a 1, that tells us we have an odd number of this character. So now we have an even number. If we use bitwise OR, it's going to stay 1. So there's actually something called bitwise exclusive OR, which we talked about, I think in the last video, which will handle this. So if they're both 1, it's going to be set to 0. If one of them was 1, if this was 1, this would be set to 1. So it works out. Now, the other thing is, while we're on the topic of this, for lowercase a, getting the ASCII value of it, subtracting the ASCII value of lowercase a is going to give us 0. So suppose we're here, we're trying to set the bit. We were thinking we'd set the least significant bit for lowercase a, but 0 exclusive OR with 0 is not going to work. Believe it or not, the way I caught this was just by having the bug in my code. So the fix for it is just to add 1, because that'll only happen for lowercase a if the character was lowercase a. So I'm just going to do a +1 here. So therefore lowercase a will map to this. And the last vowel, in the worst case, it would be 26. And we have 32 bits, so we wouldn't like have an overflow or anything like that by adding 1 to it. So that's why we're doing all of this. And with this, we're just going to do mask is equal to mask exclusive OR, all that together. The rest of this will actually be easier. So now we want to know if this mask already exists. Have we already seen this mask before? If mask is in mask to index, that means we have. And so therefore, we can compute the current window. The length of the window will be this, I minus mask to index of the current mask. So that will tell us the index that this mask first showed up. This will tell us that the index that we're currently at, taking the difference, gives us the length of the substring. We're trying to maximize it. So result will be max of itself as well as the length of the substring. Otherwise, what do you think we're going to do? If we've never seen this mask before, what do you think we're going to do? Probably add it to the hash map. So this is the first time we've seen this mask, and this is the only time we're going to be inserting it into the hash map, and this is the index that we saw it at. And I believe that's the entire code, unless I have a bug somewhere. Let me go ahead and run this. So it works and it's pretty efficient, though there is a way that we can add some slight optimizations to this code. And if I'm being completely honest, I don't think these slight optimizations are a big deal. You would probably be better off just spending your time with your family or your girlfriend or something like that. Now, if you don't have a girlfriend, then keep watching. The way our mask currently works is we're not using the lowest bits. Now, does that matter at all? Not really, but it requires us to use a hash map because the mask, it could end up being a very large value. I think U is like the 20th character, roughly the 20th character in the alphabet. Therefore, if we wanted to instead convert this hash map into an array, we'd need an array roughly of size 2 to the power of 20. Now, I don't know if my math is exactly correct. I don't know if this is the 20th character, but if it was, that's roughly correct. But if we don't want to declare a massive array for that, what we can do is stack all 5 of these towards the least significant positions. So in other words, we would want to map lowercase a to, let's say, the least significant bit 1. We'd want to map lowercase e to the second least significant bit, which in binary looks like this, 1, 0, which is 2. We'd want to map I to the third least significant bit. You might think, well, should it be 3? I mean, maybe you could kind of do that, but then you'd need to like do a bit shift down here. It's better to just set this to 4. In binary representation, that looks like this, 1, 0, 0. And so next we're going to do O, and we're going to map that to 8 because in binary representation, that's 1, 0, 0, 0. And so what I'm getting at is we can use this mapping to set the bits. This will tell us, okay, O maps to 8, therefore we want to set this bit in the bit mask. And lastly, we're going to do U down here, 16. And we can get rid of this now. The only reason I'm doing this is pretty much to convert the mask to an array. So now I'm going to create an array. Now, how long does this array need to be? Well, remember, the maximum possible states that our mask could be is 32 different states. And now that all 5 of those bits are stacked together, like if every single one of these was an odd number, the bit mask would look like this, 5 consecutive ones. That is the integer 31. Remember, 2 to the power of 5. So there's 32 possible states when you include 0, of course. So the array down here is going to be of size 32. And -1 just says that so far we have not set these yet. It's important that we use -1 here, because remember, we might see a mask at the beginning of the string S, and we'd say, okay, well, the index that we saw that mask at was 0. So we can't just default set these to 0. And also remember that at the first position, when we're mapping the empty mask, we want that to definitely map to -1. So the fact that this is already set to -1 helps us out. So we don't really need to do anything extra there. Okay, now just going through the rest of this and fixing it. So if C is in vowels, instead of doing this down here, what we can actually do is vowels of that character, because now that's going to map to a specific bit, one of these. I don't know if this is worth showing. I don't know if this is going to confuse you more, but in Python, we could actually even get rid of the if statement if you really wanted to and do something like this, .get C, and then if that character doesn't exist in the hash map, return a default value of 0. We could have also used a default dict up here. Doesn't really matter. But the reason that this works is because for any of the characters that aren't vowels, this thing is going to evaluate to 0. And so if you do 0 exclusive OR with the mask, it's not going to change the mask. So that's why that works. Now down here, we do have to change this part. We can't just do a lookup like we did with a hash map. We have to say if the mask to index of the current mask is not equal to -1. But the edge case is that that ignores the fact that, remember, there's a very specific mask. There's the mask that has 5 zeros. That's the first mask. So in that case, this condition is going to evaluate to false, but we don't want it to, because that's the empty mask. We would never want to reassign it. It should be mapped to -1 as it currently is. 0, the index 0 in here maps to -1. We never want to overwrite that. So here we can say if that's the case, or that special mask, which is equal to 0, if that's also the case, then compute the current window size. And so I believe that's correct. And then I believe this is also correct. So I think we're done here. Let's give this a shot. And so this is a very slight optimization over the previous one, but hopefully you learned something here. Check out Leetcode.io for a lot more. Thanks for watching, and I'll see you soon.